Great, so what I want to do now is just to show you more or less where we are now in the book. We're in chapter 3 for the one-dimensional problems. And so what we've looked at is essentially in yesterday's videos and finishing off this with the first video this morning, is essentially looking at the assembly of the stiffness matrix, okay, and the load vector. So that's essentially the focus was on the stiffness matrix, but whatever we did with assembly and combining was at least assembling terms into the stiffness matrix would count also for the load vector. So it's just following that numbering scheme that we spoke about yesterday. We spoke about the properties of K, just as a quick reminder in terms of what that is. We did a couple of properties that are not essentially explicitly listed here, but that are important. And then what we did is we looked at the elimination approach on page 87. So what I'm going to do is I'm going to quickly scan through this just to show you more or less where we are. Okay, so this is now chapter 3, just so that we can walk through this quickly. Okay, so this is now all things that you are quite familiar with this kind of one-dimensional kind of description of the problem. Here we see now essentially the numbering that we did for the elements, and then having sort of a global numbering scheme for the nodes, or our degrees of freedom, that they're also called. And the reason they're called degrees of freedom is at a point we might have displacement in X and in Y and in Z later on when we start doing 2D and 3D. But in 1D there's only a single unknown associated with the degree of freedom, that is, in this case, along this X direction, what is the displacement. Okay, so here it's a bit of a discussion about the numbering scheme that you can follow, which is essentially exactly what we did yesterday. And this is just relating that local numbering scheme that we spoke about to a global numbering scheme. So that is just to make sure that one understands that. So here are the global numbers, so you feel free to work through this. This is just another expose of exactly what we did yesterday. This is now done with a linear element, only 2 nodes, as opposed to a quadratic element that we did yesterday with 3 nodes. Okay, here's just some properties of the shape functions that you can welcome to work through. This is again the summation of the shape functions equal to 1. We remember what the implication of this is, making sure that that we have rigid body motion. Okay, so here's just isoparametric formulation. Here's a nice example that you're welcome to go through in terms of just make sure you can jump between the local and global coordinate system, and then compute displacements at specific place points, and strains, etc. So there's and this is now for linear elements. So this is the potential energy approach that we are not following. But what we see is essentially the outcome of the element stiffness matrices. So maybe the ones that we can, the ones that we followed was for the quadratic element. So let's get to the quadratic element. And again, I'm just skipping over this because you can really read through this in your own time. Here's the consistent no loads for the linear element, but I just want to maybe get to the quadratic element because it will be more relatable. This is the Galerkin approach that we were following. And if you get to, here's just a discussion of the properties of K. So K is symmetric. We've seen now essentially it's positive semi-definite. We understand what it means now as well. So the eigenvalues are all, there are 0 eigenvalues, so there are rigid body modes associated with some of the properties of K. So that's stuff that's quite important. Okay. Here's the elimination approach that we did. So this is just a different way of looking at it. I personally prefer the way I explained it yesterday, but you're welcome to read through this to understand what this is about. Here's just reaction forces that are solved. So here are the steps, the boundary conditions. This is known displacement, so they're given as AR. And here's just a description verbally of what we did yesterday when we eliminated or partitioned that system into the unknown and prescribed degrees of freedom. Get the system that you could solve. So this is now the solvable system, and afterwards you can compute the reactions. So that's really what this is about. Like I said, we're not doing the penalty approach. You're welcome to skip this. We're only looking at the direct elimination approach. want to get to the quadratic. Here it is. Where's the first time the quadratic multiple constraints? Here's the quadratic shape function. So this is the shape function that we've been working with the whole time. Again, let's make sure that you can quickly relate. So here are I want to just page this so you can just see for yourself how much of this you understand. This is essentially, you understand what this is. This is the psi dx, this is the u d psi, there's the q's. So this allows you then to go and compute a stiffness matrix like this. So this is the local degrees of freedom for the stiffness matrix, and you understand now how to relate that to global coordinates so that you can assemble it into the global system. What I just want to mention here, the stiffness matrix is only valid for the mid-side node in the middle. And you're welcome to use this if this is the case. So you don't always have to go and compute these stiffness matrices from first principles. If it's appropriate to use this formula, you're welcome to, but if it's inappropriate to use this formula, then you'll be severely penalized. So you need to understand what the implications are. So this is for when the mid-side node is in the middle, when E is a constant, A is a constant. So this is essentially, this tells you what this relates to. So these are the assumptions behind it, that E, so it's not just the mid-side node in the middle, but also that E is a constant and A is a constant. But as soon as E or A varies as a function of psi, then you'll have to go and compute the stiffness matrices from first principles. Here are sort of an example of the element body forces. Again, this is that split 1/6, 1/6, 2/3 that we spoke about. Again, this is only valid for a constant area and a constant body force along the length of the element. Here's just an example of some of the tractions. This is a surface traction all along the element. We looked at tractions at a cross section of the body. That was sort of a point force that we saw that resulted. Okay, so here's some nice examples you can go through where you have some global degrees of freedom. Here are the numbering schemes that you have for an element that is given in figures 3.7. It's this one here, and this is the example that we're going to be looking at. I'm going to do this example with a single element, and then I'm going to look at this example with two elements, like the case here, and then we're going to compare what our result is against the results that are given here. Okay, but here's essentially for this element with the numbering 1, 2, 3, 4, 5. Here's that global stiffness matrix for that assembly. Okay, one thing I want to highlight here is when they model the body force along this, the body force varies linearly because its body force is due to the acceleration, the fact that the thing is rotating. And so what is important to note is that they will assume a constant average body force over this element and a constant average body force over that element, which is unnecessary simplification. The way I'm going to do it is I'm going to show you what happens if you model the body force linearly varying. Okay, so we're going to model it linearly varying, and then I'm going to show you how that differs from if we were to do like they've done here, sort of a piecewise constant over the two elements. Okay, this is just to make sure that we understand the difference. But what is important in this course is when we compute body forces, always we're going to compute it consistent. We're not going to just assume how it splits, because I've already demonstrated you what the consequence of that is. So just for clarity, body forces will always be modeled in this course as consistent unless I explicitly tell you to do something different. Okay, and when the body forces vary as a function of some parameter, you need to model it with that variation and not do the simplification that they've done here. Okay, unless I explicitly tell you to do the simplification. So this is just to make sure that we have a good understanding of an agreement with how we're going to treat this. But this is just to give you an idea, because they've treated this F1 and F2 now as constants over those elements, they were able to use this closed form expression. But I would like you to, if the body force varies linearly, you need to go and compute what is that split for a linearly varying body force. And that's essentially what we're going to be looking at next in terms of the Python code. So please work through this example before you start watching the Python videos that will follow next. Because this example will solidify on pen and paper what we're just going to implement, and we're going to make 1 or 2 changes to the way that we implement it here so that we can compare it sensibly and interpret it critically. All right, thank you.